All right, everyone. Chapter 3.3. Now that we have looked more detailed into linear and logistic regressions, I would just briefly, really on one slide, showcase three other model types or modeling types that are important. And just to maybe that you have heard the name once, or that to wake your interest, or if you have an application, you know what to Google. And then give some really, really important remarks before we really get into modeling. All right. First thing I wanted to show you is time series analysis or time series modeling. Obviously, it's already in the name. The application is to model patterns for time-based data. We will just take a really quick look. We neither have the time nor expertise to touch all of this really in too much detail. But for everything, great materials exist, of course. If you're interested, look that up or hit us up and we can share some cool materials with you. So this type of modeling is basically meant to take a temporal dimension into account. So here, for example, if we would like to model the quarterly earnings per share in this example of Johnson & Johnson, and we have the time factor needs to be taken into account. We can do time series modeling. We get a similar regression line, but here we can do this regression over time to do better predictions. Won't go too much into the statistical or mathematical details. Decision tree modeling is also a really, really nice method. The application here is to look at nonlinear relationships or even that also include multiple interaction between independent variables. So really, let's say, complex relationships between independent variables. And how you do this is you just split up your data based on the most informative independent variables. So they are sometimes called featured, especially in the area of deep learning or machine learning. And you do that in order to predict the outcome variables. So here you split up, for example, your feature x1, independent variable x1, in values smaller or equal to 3 and larger than 3. And then you split again. This is what you call the tree. And in the end, you get a model, you estimate a model that predicts your outcome variable. And the third point, really relevant nowadays, and I think you will for sure have heard of it, deep learning, sometimes used equivalently with machine learning, but let's stick to deep learning for now. The application here is to learn from and make predictions about complex and high-dimensional data. So data that is beyond our understanding in size, in complexity, and in dimensions, so a number of variables, let's say that. We can use deep learning algorithms to estimate models and with the application of making predictions. So here, this is just a very basic setup how a neural network, which is used in deep learning, is created or estimated. You have an input of your features or your independent variables, and you have then something that's happening in between. I won't go into much detail. We'll talk about it in just a second. And in the end, you will have an output, which is your prediction or prediction model of the outcome variable. If you would like to understand that, and even if maybe you're not specifically interested in that, I can highly recommend a video by a great YouTube channel about how neural networks work or function. I think it's really, really great, and it's totally worth taking the time to understand that, especially with the increasing importance of deep learning and LLMs like ChatGPT and so on. I mean, it's not the same, but it's great to understand how neural networks work. And now we would like to look at models in R, but before we do that, I think there's one really important small section. Some remarks of caution, which I would like to give you before we try to interpret and jump into the models. In general, in my opinion, regression models are great. We can make great use of them, but there are really a bunch of pitfalls that we would like to avoid, or stuff that can heavily go wrong if we don't think about it. First of all, if we design our model, so if we try to find out which independent, which dependent variables we would like to use, we don't want to do this according to the so-called kitchen sink approach, which means as independent variables, you just throw in every variable that you have in your data set, or you just throw everything and just hope that you get a good model. Adding an independent variable to your model always need to be justified by theory. So if we look at life satisfaction and I want to use a shoe size or a favorite color as independent variable, I have to make a theoretical claim why there could be a connection between these two variables. I can't just throw in every variable in my data set in there. And something that often happens in combination with that is just fishing for correlation. So I could just throw in zillions of variables in my model and then hope for highly significant and great correlation coefficients that are just correlations, and then say, yeah, and then have our results sections in a research paper, for example, and state that we found great and highly significant regression coefficients. But that's not how it should work. So the addition of an independent variable of a model should always be driven by the theory. And also then the interpretation of your coefficients. It's really important to make correct statements on the interpretation for linear regressions, for logistic regressions, basically for every model. We'll talk about this later in one of the videos on modeling in R, how to interpret regression outcomes. Then it's highly important, also correlated with the previous slide. Correlation versus causation should never be mistaken for each other. Only because two variables are highly correlated or we have a highly significant coefficient, it doesn't mean that this is the same than a causal effect of independent variable on dependent variable. As a oftenly used, but in my opinion, really great example, there's a website that shows these so-called spurious correlations, variables that are highly, almost perfectly correlated. You probably can't read it, but these two variables here have a correlation coefficient of 0.99, almost perfect correlation. But if we look at it, it's the divorce rate in Maine and the per capita consumption of margarine. You cannot convince me that there's a theoretical connection between the divorce rate in Maine and the per capita consumption of margarine. This is just spurious, or let's say it occurred random. We cannot mistake this for causation and say that the divorce rate in Maine is a major driver of the consumption of margarine, or the other way around. They are correlated, but they don't cause each other, these variables. This is a really important distinction that we always need to make. And also, I just said you cannot convince me that these two are somehow theoretically connected. It refers to, I would say widely used or widely, unfortunately, applied a thing called fishing for theory. So people would just estimate their models with the kitchen sink approach, throw in all the independent variables, and then find maybe some significant coefficients, and then just fish for theory. So even if you find unexpected results, you could spend hours and days to try to make up a theory why these two are correlated. Like I could now sit here and say, okay, if people get divorced more, maybe then they are unhappy and they like to consume more margarine because they like to eat greasy food after their divorce. But this is just fishing for theory. There was no, so it was not suggested that there was a theoretical connection between these two beforehand. So I just want to caution you, don't fish for theory, don't mistake correlation for causation, don't fish for correlation, and we'll talk about this point later. Make correct statements and correct interpretations of your correlation coefficients. So now that we've established some caution, I definitely don't want to ruin all the fun of statistical modeling. Let's, in the next video, take a look at this in R.